Hello, welcome to video number 5 on power. So power for us in physics is a measure of the rate at which energy is being used, or the rate of energy output. And we could also say it's the rate at which work is done, because energy is work, and it's also the rate at which energy is transferred or transformed, rate at which energy is being used. And because it's a rate, and because the standard unit of time in physics is a second, the rate is usually per second. And so the units of power, strictly speaking, would be joules per second. Joules per second to the minus 1. Because energy is in joules and it's a rate, so it's per second. Now, however, we know that 1 joule per second is also called a watt. And we've used a watt before when we did electrical energy, and that's a W, not to be confused with the W for work, which you find in your formulas. Now the watt comes from, it's in honour of James Watt. I might not have mentioned this when we did electrical power, but he was a Scottish physicist who invented the first steam engine. What did he look like? Very much like James Cook. And what did his first steam engine look like? Try and picture it. Look like this. Basically, it was very simple. A vessel that had steam in it, a cylinder, and some valves that caused this to rock or pivot around this point, and then could do work here. And basically, it was a pump. But it was very soon transformed into a more powerful and elegant design, and eventually someone put it on wheels and made a railway engine out of it. But it was also used to power all the mills, and before the steam engine, all the cotton mills and wool mills and things like that, and grain mills, they were all powered by water wheels. But then the steam engine came along, and so they could build factories anywhere, and predominantly where there was coal, because the coal would fire the steam engines. So we have the formula power equals W on T, where power's in watts, work's in joules, and time's in seconds. And because the work is a change in energy, we can say that it's equal to this divided by T. So that's the change in energy in joules. And that gives us lots of possibilities, because the change in energy could be in any form of the energies that we've been talking about. So that means that we can calculate power from what I just said. And if the change in energy is a change in kinetic energy, we could use the half mv squared as our change in energy. Okay, but the change in energy could be a change in potential energy, or gravitational potential energy, in which case we'd use mgh, and it would be divided by the time in seconds. Now we'd also recognize, and this isn't one that's on your formula sheet, but we would recognize that P equals W on T. We know that work equals Fs. So that's where this comes from. Okay, so the work could be just applied force times the distance the applied force is being applied. So that's another one. Now that's not on your formula sheet, but this is, and this is. So you just need to be able to combine them. We also would recognize that we can get this formula here. Now where's this one come from? Well, we recognize, if we had on our information sheet, we have V equals S on T. So here we have S on T, so that's, we can replace S on T with V, and V, just this little C there, means constant, because we're not talking about acceleration. This force is not causing an acceleration, it's the applied force that's causing the movement across this distance in this time, resulting in a constant velocity. And I think if I press a few things here, some arrows appear, okay, which explains that. Now this one and this one is not on our information sheet. Neither is this one nor this one. But if we look on our information sheet, they're all there in one form or another, and the one I'm missing here is V equals S on T, and so we should be able to combine those depending on what the question's asking us and what we're given. Let's have a go at a couple of examples. What is the power output of a cyclist who transforms 2.7 times by 10 to the 4 joules of energy in 3 minutes? Minutes, that rings a bell, doesn't it? So power equals work over time. Work is in joules. We've got joules here, so we put that number there. We've got to convert the time into seconds, and so it's 150 watts. Little trick in that one, well, a couple of tricks actually. What about this one? A 52 kilogram student runs up a flight of stairs of vertical height 3 meters in 4.7 seconds. Calculate the power. So if you're running upstairs, you're after the power, you've got the work, you've got a time, but you've got to ask yourself, what is the work, what sort of work is done? And in this case, the work that's being done is a change in gravitational potential energy. So, because we're raising the student 3 meters up, and so that means that the work done we replace with the formula for gravitational potential energy, mgh. Put the numbers in, remembering we use 9.8, and you get 330 watts. Now if you come down those stairs, that's how much energy is being converted from gravitational potential energy into other forms. Now you have these questions to have a go at in your workbook, and you also have a whole lot of power questions. Next one we'll be doing the conservation of mechanical energy. See ya.